This is a radioactive material in a cloud chamber. Those thick white lines you see are the vapor trails of alpha particles shooting off the sample at about 5% the speed of light. But Einstein saw a contradiction here. If the math of quantum mechanics is right, these particles shouldn't travel in straight lines at all. Their waves should spread out spherically in every direction. This contradiction is called the Mott problem. I'm going to show you how the solution to this problem challenges our very idea of reality. In 1927, some of the greatest scientific minds in history gathered in Brussels for the 5th Solvay Conference in Physics. This is a meeting that would forever shape our understanding of reality. I mean, can we just stop here to appreciate this picture? This has been dubbed the most intelligent picture ever taken. I mean, we've got Erwin Schrödinger, Wolfgang Pauli, Werner Heisenberg, Paul Dirac, Louis de Broglie, Niels Bohr, Max Planck, Marie Curie, and of course Albert Einstein. During this conference, Einstein repeatedly argued that quantum mechanics couldn't be the final word. He refused to believe that nature was fundamentally random. This would later be summed up with the one line attributed to him that says, "God does not play dice with the universe." But a lesser-known problem was also proposed by Einstein during this meeting. Einstein described a radioactive atom emitting an alpha particle inside a cloud chamber. According to quantum mechanics, the alpha particle's wave function should spread out equally in all directions, forming a perfect sphere. But when you look, you don't see a sphere of droplets, you see a single straight line. So Einstein asked, how can the corpuscular nature of the phenomenon be reconciled here with the representation by waves? Basically, he said, why do we see straight lines when everything in the theory is a spherical wave? This question wouldn't be adequately answered for years, and it's now called the Mott problem. It's present everywhere, actually. Every time we record a particle, it shows up as a track or a line, never a smeared out wave. For example, watch what happens when you inject radioactive radon gas into a cloud chamber. If the alpha particle's wave functions are all spherical, why doesn't the whole cloud chamber just fill up with a mist? Why do we see these distinct straight lines everywhere once the gas is introduced? An alpha particle is basically a helium nucleus, 2 protons and 2 neutrons bound together. Before it's emitted, it's trapped inside the nucleus of a larger atom by a nuclear potential. Inside, it behaves like a standing wave confined by the potential, but occasionally it tunnels through the barrier and escapes. That means if we constantly checked where it was, we'd usually find it inside the nucleus, but every once in a while we'd find it outside the nucleus. And once it escapes, its wave function becomes a traveling spherical wave expanding outward in all directions. And because the nucleus is nearly perfectly spherical, there's no preferred direction, so the emitted wave spreads out equally everywhere. And herein lies the problem. In reality, we don't see the alpha particles triggering the cloud chamber mist in a sphere around the source. We see them shooting off in straight lines. But why? Well, a brilliant physicist named Neville Mott set out to solve this problem. 2 years after Einstein proposed the question, he published a paper called The Wave Mechanics of Alpha Ray Tracks. In this paper, he said that the discrepancy comes from the fact that we're viewing the wave function of the alpha particle as if it were the only wave function that exists. However, in reality, there are other atoms in the chamber which also have their own spherical wave functions that interact quantum mechanically with the alpha particle. And together they form a single entangled wave function. Since the mathematics were so intense, and this was way before any computer simulations, Mott took only 2 atoms plus the alpha particle. In this new wave function, he found something surprising. The probability wasn't spread evenly anymore. Some regions of the sphere were even more likely than others. Later, scientists found that the more atoms you add to the mix, the more defined these areas are. So the wave function becomes striped. There are streaks of almost 0 probability and streaks of higher probability. So by adding a bunch of wave functions together, you end up with classical streaks and not evenly spread out probabilities. So this answered the question of why we always see clear streaks of particles, because they're always interacting with their environment. This idea that smeared out probability always ends up as clearly defined paths is now called decoherence. Decoherence tells us that once the alpha particle takes one of these paths, it can no longer interfere with any of the other paths. So you couldn't do a double slit experiment or anything like that with the particles. They act like defined paths that can't interact with other paths. But there's still a problem that decoherence doesn't solve. I showed you that when you add all the wave functions of all the atoms in the environment together with the alpha particle, you get a wave function with streaks, areas of high and low probabilities. But there are still many of these streaks for just one alpha particle. In fact, the fully decohered wave function doesn't pick one path. It predicts an infinite number of possible straight line tracks, equally likely in all directions. But which path does it take? Well, decoherence can't tell us that. In fact, nothing can tell us that. Any direction is equally probable. It's completely and fundamentally random which streak path it takes. I love the Mott problem because it clearly shows that decoherence answers the questions of why we get streaks or straight line paths, but it does nothing to answer why we get the particular path that we got. This problem is called the measurement problem. Many people mistakenly believe that the measurement problem is solved by decoherence. But Einstein's original proposal still stands. Does God play dice? Is our universe fundamentally random? Or is there some metaphysical hidden variable that we have yet to find that decides the decohered wave function path? I don't know. Until then, I'll just continue to watch my cloud chamber, knowing that as far as we know, nothing can predict where the next particle will decay. And also, before I end, I want to make another point that many people get mistaken. There's an interpretation of quantum mechanics called the many worlds interpretation. In the context of this alpha particle decay experiment, it says that out of all the possible straight line paths, none of them is uniquely chosen. Instead, every possible path happens, each in its own separate branch of some universe. In this view, there's no special collapse event where one outcome is selected and the others disappear. The wave function never collapses, it just keeps evolving, splitting into countless versions of reality. So this interpretation says that everything that can happen does happen somewhere in some unreachable other universe. But this raises its own problems. If every possibility occurs, then what does it even mean for something to happen? The interpretation never clearly defines what counts as a separate branch or when one branch becomes distinct from another. For example, in the case of a decohered alpha particle, its direction of travel is a continuous variable. That means that there are infinitely many possible directions it could go, uncountably infinite, even after decoherence. But that's a problem because in the real world, we don't see infinitely many distinct paths. Two directions that differ by just a quadrillionth of a degree would leave identical, indistinguishable marks in a detector. So decoherence doesn't fix this, it only tells us when paths stop interfering, not when they become separate universes. And also, there's no clear rule in the many worlds interpretation for when two almost identical outcomes count as different worlds. This is known as the preferred basis problem. So saying there are infinite universes doesn't solve the problem, it just hides it behind infinity. It replaces one mystery, why this outcome, with a bigger one, why infinite outcomes we can never define or detect. The many worlds interpretation avoids the collapse problem, but it doesn't solve the mystery of why our universe gets the result it does, which was the original question to begin with. And the theorem does so at the cost of introducing an infinite number of universes that could never be proven to exist anyways. So beware of using the many worlds interpretation to solve the deepest mystery of quantum mechanics. And thanks for watching another episode of the Action Lab. If you haven't subscribed to my channel yet, remember to hit that subscribe button, and we'll see you next time.